Hi everyone, I'm going to present to you today the work I've been doing recently during the last 12 months with Bruno Barras and Frédéric Blanqui and other members of Deduct team. Deduct team is a mixed INRIA, CNRS, ENS Paris-Saclay research team located at the LSV, Laboratoire de Spécification et Vérification. And the Deduct team conducts research in the field of mathematical logic, proof theory, proof assistance, and more particularly, the team is specialized in the interoperability of proof systems. So the plan of this talk is gonna be the following. First, I will say a few words on why we want to prove things and what do we want to prove. Then I will recall some basics about type theory and dependent type theory and try to present succinctly a logical framework the Deduct team push forward as a good candidate for proof interoperability. In a second part, I will present another point of view, or maybe a complementary point of view, the possibility to use this particular framework directly to prove things. So I'm gonna recall what a type theory-based proof assistant is and what it means. In a third part, I will give an example of a work of formalization that takes advantages of this framework. And in the last part, I will present a particular feature we are working on in Deduct, the possibility to interact with the so-called unification goals. And finally, I will give some perspective on this work. So, introduction. So, if we think of the obvious industrial applications, proofs arrive through proof obligations in specified software. It is one way to ensure that there is no bug. One cannot indeed remove all bugs from software just by adding tests. Even with a substantial amount of tests, bugs remain, and that is unacceptable with critical infrastructures. We want also to prove pure mathematical statements. One can think of various complex proofs which have been checked during the last decades. For example, the Kepler conjecture, the four-color theorem, the odd-order group theorem. So let's also mention that it was an error in 1991 proof which stayed more than 20 years, which motivated Voevodsky to shift his research from algebraic geometry to homotopy type theory and develop the so-called univalent foundations. We could also mention a proof of a famous arithmetic conjecture, the ABC conjecture, which has been published during the first lockdown, but is considered as flawed by the majority of the experts in algebraic geometry and arithmetic. So it would be nice to imagine a not so distant future when the mathematical articles will be submitted directly with their proofs in a proof assistant. So let's say a few words about type theory. In type theory, the notion of type is primitive. There is no pre-existence of objects without the type. There is no heterogeneous collections. And functions are given explicitly, contrary to the set theoretic world where functions are defined as functional graphs. In type theory, one doesn't need two layers as in set theory, where you need proposition plus sets axiomatized in first-order logic. On the contrary, type theory is its own deductive system. So type theory is well suited for computers because of its rigid constructions. Let's say also a few words about the Curie-Howard correspondence. Here the types are interpreted as theorems or propositions, and the terms are interpreted as proofs. So proving a theorem in this framework is like constructing an element of this type. And the type formation captures the logical operation. For example, if you look at the violet line in the table, you will see that the interpretation of the function type with the arrow is interpreted as the logical implication. And if you look at the line below, the dependent product is interpreted as the logical universal quantifier. Some of the extensions of the simply typed lambda calculus, here in the bottom left of the Brown-Dracht cube, can be classified depending on their expressiveness. So, for example, here less expressive is on the bottom left, and the most expressive is on this picture, and complicated one is in the upper right. And the foundations of the proof assistant cog, for example, are an extension of the calculus of construction in the upper right on the picture. Here, in this talk, the ones that are going to interest us particularly are the two in the bottom right, the Lambdapi calculus and its extension modulo rewriting. With this language, you have the possibility to specify the function taking two, for example, the function taking two vectors and returning the concatenation of the two vectors. So suppose you take a vector of size n and a vector of size m, concatenate them, and you obtain a vector of size n plus m. But sorry, there is a mistake on this slide. The interesting part is that the n and m are not constants. The size of the result of this function is depending on the arguments. So the size of the return vector is specified, and m and n and m are variables, and the size of the return vector is specified anyway. And this Lambdapi calculus is also known to logicians as LF for logical framework, because it is used to encode other theories. Here's the inductive definitions of the lambda terms of the Lambdapi calculus. The syntax is pretty simple compared to other systems. You have two sorts, type and kind, variables, applications, abstractions, and the dependent product. And here we consider an extension of this framework where you can define function and type symbols with rewriting rules. So in particular, you have this extended conversion rule that allows you to have, if we go back to our vector example, to a strict equality between vector 2 plus 2 and vector 4. It is not a proposition to prove where we should keep in mind the witness of the proof. It is a strict equality. And if you constrain the collection of rewriting rules, the fact that they preserve the typing, the fact that they should form a normalizing and confluent rewriting systems, properties that can be checked by specific tools. So if you have these properties, you get a strict conversion with decidable type checking. So this framework has several advantages. It is simpler than Coq, but it is powerful enough to encode and check proofs developed in other systems. So it is a natural choice for interoperability, as it allows you to translate proofs from a system to another. But it also opens the possibility to build proofs, assembling lemmas coming from different libraries, from other systems. We can even imagine an encyclopedia of mathematical proofs which can be exported in an arbitrary system on demand. And this is precisely what the Logipedia project is trying to achieve. So currently, Deducti2 is an implementation of the type checker and comes with the translation tools. But there is a complementary point of view on this. Why not using directly this framework to formalize mathematics? If you want to formalize complex proofs in this framework, one has to extend a basic type checker to a full-featured proof assistant. So what does it mean? With a type checker, one has the ability to infer the type of a term. This is called type inference. You can also check that a term has a particular type. This is called type checking. Can also compute a term relatively to the beta reduction on the rewriting rules and check the convertibility of two terms. A proof assistant does more. One can build terms incrementally. This possibility to build terms we would like to be of a particular type, the target representing a particular theorem, it's what we are going to call inhabitation goals. And the methods and the reasoning behind the terms we would like to be equal, we are going to call these unification goals. And the methods we are using to manipulate these goals are called tactics. So this work is about using deductive free, a proof assistant with these inhabitation goals, to formalize categorical models of type theory, and adding unification goals feature alongside the inhabitation goals. So about this example of formalization, let's say a few words about model theory in general. Roughly, this can be think as the theory of the relations between theories. It is used to prove, among many things, coherence of a theory and dependence of a particular axiom, etc. It also provides some interpretation to a language, for example, a geometrical interpretation. More specifically about model of a particular class of type theories called intentional dependent type theories, they have identity types representing the propositional equality with a behavior that is similar to the geometrical paths in homotopy theory. This is why we are interested in the formalization of the category of simplicial sets. The objects of the category, named here delta, are just finite, non-empty natural numbers, and the morphisms are simply the order-preserving maps. So this category has a combinatorial nature by its definition, but has the very important property that it has the same homotopy theory as the one of the usual topological spaces. But usually, these models rely on set-theoretic foundations. So especially because one of the goals of intentional dependent type theory is to build new foundations to mathematics through the univalent foundations, it would be interesting to model type theory inside type theory without relying on external foundations. And simplicial sets are known to be difficult to formalize because of the so-called coherence conditions. This drawing is one way to understand them. Consider a triangle, 3 edges and 3 vertices. So 1, 2 simplex, 3, 1 simplices, and 3, 0 simplices. One property you want to formalize is the equality between the borders of the triangle with the edges and the borders of the edges with the vertices. And the propositional equality of intentional type theory will complicate things because you will have to prove the equality and prove the proof of equality and prove the proof of the equality, etc. This is where deductive can help. The equality is strict and the type checking remains decidable. So for now, we have formalized in deductive free the category of semi-simplicial sets. And this has been turned into a model of a non-dependent type theory, system F. This work is exposed in the Book of Abstract of the Types Conference of this year. But this is not sufficient. To reach the formalization of a model of a full intentional dependent type theory, validating the univalence property, we need to formalize the notion of category with families and extend the category of semi-simplicial sets to the one of simplicial sets with the degeneracy maps and also the simplicial sets with the can condition. The degeneracy maps I'm talking about are related with the fact that in our formalization, we consider only, for example, only a true triangle, not degenerated flat ones where two sides share the same vertices. So this has been tried by Bruno Barras on Deducti 2, but it turned out to be impractical without a real proof assistant and the equational reasoning we were previously talking about. Indeed, the errors one can get are really cryptic and hard to understand with these kinds of models. So one really needs interactivity with unification goals. So now I'm going to describe this experimental feature we have recently added in Deducti 3. I will show how the current proof mode is working in Deducti 3. But briefly before, let's say a few words about LSP. So LSP is the language server protocol. It resolves the so-called matrix problem between IDEs and the programming languages. Usually with plugins or configurations not based on LSP, you need to configure each environment times each programming language. And this is a terrible waste of time, and this is not reliable. With LSP, it's different. The user stays in his or her favorite IDE. The IDE designer focuses on the LSP client side, and the language designer, here the Deducti 3 developers, focuses on the LSP server side. So they just have to respect the basic protocol and talk to each other through textual JSON documents. This protocol defines the basic features you can dream of when developing, jump to the definition of a particular symbol, completion, general notification, etc. So currently, Deducti 3 is well integrated with Emacs and VS Code. And these two environments share the same LSP server that could be used for other editors as well, VI, Sublime Text, or whatever. So let me show you how the proof mode of Deducti 3 currently looks like. This is Emacs, and this is a good moment to look a bit at the syntax of Deducti 3. So we are going to prove a very basic arithmetic theorem from scratch. So we define the natural numbers in the usual way with the two constructors, 0 and the +1 function. Defining the addition shows already some specific characteristic of this framework because we define first a symbol for the addition. Only later, when you want, when you need it, as you work or formalization progress, you add a collection of rewriting rules defining the values of the functions. The multiplication is done in the same way. And we have added at the end necessary for the logical part, a type of propositions on an equality between natural numbers with the property that a natural number is equal to itself, which is called reflexivity. So you now have a hint on the syntax of Deducti, but these are only declarations, and there is no interactivity for now. So let's prove a very simple theorem, the fact that 2 times x is equal to x plus x. We don't want to declare a theorem, we want to prove it. So we want to build this lambda term. So we go in the proof mode, and we write our first tactic. We have to destruct the product indexed by x. So we introduce x thanks to the assume tactic. You can see that there is no a goal buffer in Emacs. Deductive free infers the type of X. It is a natural number and it is put in the hypothesis above the dashed lines. And the goal has changed compared to the initial theorem. Then we use the simplified tactic. It computes the 2 times X following its definition and transform it as X plus X. Then we use we have an equality between the two identical terms, syntactically speaking. So we just use the reflection symbol we have been talking previously, and the proof is finished. So now let us put on purpose an error in our theorem, trying to prove that 3 times X is equal to X plus X. So obviously this is wrong, and deductive free won't be happy with it. We apply the proof script we have just used, and we see that there is an unsolved goal. The reason why I'm showing this very simple example is the following. You can imagine that what could happen if one was formalizing categories with families, universes, which are types of types, simplicial sets, and etc. You can get easily in trouble with very hard to correct errors. So in this simple example, deductive free hasn't been able to solve the goal, but it is really a conversion problem. So unification can fail if the user made a mistake, for example, because the type is not well formed. On the default unification algorithm can fail too. So a solution, if everything is going fine, typing plus unification, the proof script should not be mandatory. But if unification fails, deductive free should not fail immediately with cryptic error. It should allow to enter in the proof mode, a new extended proof mode with both unification problems treated as the usual inhabitation goals, and new kinds of problems that should be resolved with tactics. And because unification can fail, even if there is nothing special to prove, this proof mode has to be accessible for symbol declaration and not just only theorems. So even better, at some point, the user should be able to interactively tune the unification algorithm. So really, the tactics should be pieces of the unification algorithm. So if for now, we have recently added these unification goals. So let's go back to our wrong arithmetic theorem, but this with this experimental feature turned on this time. We can see in Emacs that there is now 2 types of goals. One with the unif keyword corresponding to unification goals, and one with the typed keyword corresponding to the usual inhabitation goals. So we have here a new goal printed, a trivial unification one. It comes from the fact that X has been inferred by deductive, and it has to be a natural number. And the default unification algorithm has now been turned into a solved tactic. And we see that the unification goal has disappeared. And then we do the rest of the demonstration as we were before. And at the end, we can see now that what's the problem is that there is an unsolved unification goal. So the error is more clear than it was previously before. But if you apply the global solve tactic, you won't be able to go deeper in the problem. So this is still primitive, but because we need 2 things: the ability to have pieces of the unification algorithm, so that we can go deeper in the problem, and we also need a user-friendly way to name the goals and go back to the location of the initial problem. But still, this way, this opens the way. It opens the possibility to interact with unification. So let's conclude. Deductive is a natural choice for interoperability because it relies on the Lambdapi calculus modular rewriting, which is a simple but powerful logical framework. Deductive can export proof from a system to another. Deductive free is a proof assistant with tactics suitable for proof development. Its user interface is gradually improving. And the Emacs and VS Code integration uses the state-of-the-art LSP protocol. This work makes contributions to a library formalizing the category of semi-simplicial sets on the model of a non-dependent type theory, system F. This has been exposed in the Types Book of Abstracts of this year. And we recently had the possibility to manipulate unification goals in deductive free. So to finish the work in progress, continue to investigate the formalization of a simplicial model of intentional dependent type theory and write accordingly unification tactics. Thank you.